Hello, everyone, and welcome to today's webinar on metal-based additive manufacturing, 3D printing, metallurgy, and processing science. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Jim Curiel, Senior Consultant Metallurgist at EAG Laboratories, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Dr. Kin-Ling Sham, Senior Consultant Metallurgist at EAG Laboratories.
Thank you, Rena. Good morning, everyone. In today's webinar, the topic we will talk about is metal-based additive manufacturing, also more commonly known as 3D printing, and give many examples on how the processing science can affect the final printed part with a focus on the metallurgical effects. My name is Kin-Ling Sham. I am a Senior Consultant Metallurgist at Eurofins EAG Material Science. I have over 8 years of experience in metallurgy, welding metallurgy, and material characterization. I have worked on projects related to welding consumable development in order to control metallurgical and mechanical properties desired, offshore structures, nuclear submarines, and additive manufacturing, to name a few. Here is a brief outline of today's webinar. I will give an introduction to EAG for those of you not familiar with us. Then I will introduce the 4 categories of metal-based additive manufacturing. And then examples will be given on how the processing science in metal additive manufacturing can influence the final printed part. All examples are techniques and metallurgical expertise that EAG can provide clients to assist in understanding how to print a part with the desired properties for a specific application. EAG Laboratories has several hundred highly educated and experienced employees working in laboratories around the world. EAG offers over 40 analytical techniques with metallurgical investigations offered at our Los Angeles location. The LA EAG team has the capability and expertise to assist in any type of metallurgical and material engineering difficulties in additive manufacturing, and empower clients to better understand the effects of the processing science on the final build. EAG was established in 1978. Our expertise, combined with leading state-of-the-art technology equipment, enables us to leverage the power of science and engineering to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. Let us begin by defining additive manufacturing. Additive manufacturing, also known as 3D printing, is a diverse set of processes that take feedstock in the form of powder, sheets, or wire to create a 3D part, either by melting or solid-state joining. According to ASTM, there are 4 metal additive manufacturing categories: powder bed fusion, direct energy deposition, binder jetting, and sheet lamination. Powder bed fusion are all processes that have a focused beam energy that fuses selected regions of a powder bed onto a build substrate or a starting plate in order to give structural and thermal support to the build. The production time is long, but the dimensional accuracy is better than most other additive manufacturing processes. The 2 processes in this category are selective laser melting and electron beam melting. The second category is direct energy deposition. These are all processes where a focused thermal energy creates a melt pool in which material in the form of powder or wire is deposited. The heat source can be in the form of a laser, arc, or electron beam. This category has origins from traditional welding technology. Therefore, many established concepts from welding can be used to study and explain the final build using direct energy deposition. The next category is binder jetting. This is a non-fusion based process and uses a liquid bonding agent deposited via an inkjet print head to join powder materials formed layer by layer until a green body is formed. Then the green body is post-processed by consolidation, removal of the binder, and sintering. The loosely packed metallic powder is sintered together through powder particle-to-particle neck growth and densification. Parts are printed larger to allow for shrinkage during sintering. The last category is sheet lamination. This process is the stacking of metal sheets that are bonded to form a 3D part. Final cutting on the final part is needed to achieve the desired geometry. So, how do we print a metal additive manufactured part with the desired properties for a distinct application? Well, from physical metallurgy, we know that in order to achieve the desired mechanical properties in a material, the chemistry, microstructure, and defects need to be controlled. From welding metallurgy, we know that all welding process variables and inputs, such as power, speed, beam interactions, heat transfer, process temperature, wire chemistry, base metal chemistry, preheat, interpass temperature, and more all help control the thermal and physics interactions that subsequently determines the solidification kinetics, phase distribution, phase transformation, crystallographic orientation, and grain morphology, which dictates the properties of the material. So here we see process inputs in additive manufacturing. This includes the energy source, the part geometry, the scan strategy, the feedstock quality, and the build chamber. These process inputs then affect the thermal interactions, which includes the applied energy type and size, the heat transfer, cooling rate, and process temperature. Both the process inputs and the thermal interactions come together and determine the layer bead morphology, the solidification, the microstructure, and the defects, which in turn then produced the additive manufactured part with the desired mechanical properties. EAG can help determine what caused the defect or why the additive manufactured part does not meet the desired mechanical property requirements and help solve problems until the clients can achieve their desired final build. One of the most important aspects of getting a desirable final build is starting with the right feedstock. It is pertinent to have optimized chemistry of the feedstock, regardless of form, whether it be in powder, wire, or sheet. Additionally, size, shape, morphology, particle distribution of the metal powder is also important to achieve an optimized final build. EAG not only has many chemistry capabilities, but also capability and assist in looking at the size, shape, morphology, and particle distribution. So in this slide, here's an example of how knowing more about your feedstock can help you achieve a better quality final part. So here in the top two images, we see two types of powder, metal powder. So these powders are the same composition. They're both Inconel 718. However, the difference between these powders are visible through these SEM images. The one on the right are nice and consistently spherical and similar in size. The one on the left have more morphology variations, have porosity and surface phenomena, and also are inconsistent in size. So now, using the same powder composition that are manufactured differently, and this is what these SEM images show, while keeping all other input parameters the same, two different final parts were produced. This image below here, down on the left, shows one that has tremendous porosity. The one on the right shows one that is nice and solid with minimal porosity. Why is this? The reason is these two powders were manufactured in different ways. And the two different ways are, one is plasma rotating electrode process, and the other is gas atomization. So the one on the right is manufactured via plasma rotating electrode process, and the one on the left is using gas atomization. Gas atomization is known to have porosity within the metal particles. Therefore, oftentimes it is translated into the part. Another important aspect to consider is the surface roughness in metal additive manufacturing. Surface roughness is limited by the layer thickness and the degree of inclined surface. For better surface roughness, thinner layers and therefore longer print times are needed. Another method to improve surface roughness on complex parts is to design the part to avoid sharp build orientation angles by optimizing build direction and scan strategy. So here, looking at image A, we can see if we change the build orientation, we can have a smoother surface finish. In image B here, we can see this graph shows the x-axis as layer thickness and the y-axis as average roughness. As layer thickness increases, average roughness increases. If you look at this image on the right here, this is a 17-4 precipitation hardened stainless steel. By using thinner layers, we are able to minimize the surface roughness here. Now in image C and image D, this demonstrates another surface roughness effect known as balling. When the heat input is low, insufficient energy is used to fully melt the powder particles, and they stick on the surface of the part. In image C, you see powder particles on the surface of the final build. In image D, you see large degree of balling these powder particles on the edge of the weld pool. Optical and SEM imaging can be used to detect the balling effect. For image D, the balling effect occurs on the side of the weld. At high laser scan speeds, the molten pool can become elongated, which can increase the surface tension gradient-driven flow inside the molten pool, and therefore drag these unmelted powder balls to the edge of the weld pool. Now let's look at these last two images on the bottom. The one on the left, image E, the x-axis has heat input, and the y-axis is surface roughness. So as heat input increases, surface roughness decreases. Now this image on the right, image F, we have on the x-axis average powder diameter, and on the y-axis surface roughness. So as average powder diameter increases, so does surface roughness. And the reason because of this is because larger particles are typically more difficult to melt. In additive manufacturing, density is an important part to measure. EAG can assist in enhancing density in printed parts by measuring density of the feedstock and parts. The two ASTM standards used for testing density of powders, green parts and final parts, are ASTM B962. This is standard test method for density of compacted or sintered powder metallurgy products using Archimedes principles. And the other one that is used for feedstock is ASTM D7481, standard test methods for determining loose and tapped bulk density of powders using a graduated cylinders. Both of these techniques are available at EAG. So you might ask, why is density important to measure? Well, as density is increased, porosity is decreased, and therefore mechanical integrity is enhanced. Bead morphology of each printed layer is another important consideration. Bead morphology can be controlled by both additive manufacturing process inputs and thermal interactions. Bead and layer morphology can be affected by the molten pool shape and discontinuity in the deposited bead. So here in image A, we see surface depression and unfilled spots, and then we see a hump, and then we see another unfilled spot here, and then another hump, and an unfilled spot, and another hump. So we can see the cross-section of A here on our right, and the cross-section of B here on our right. So A, you see this lack of penetration with this hump, and B, you see a lack of deposit material. Hump formation is common in high-speed arc welding used in direct energy deposition. It leaves open and unfilled spots in the length of the layer, thus creating what we call as hump heads. The front of the molten pool shows a depression called the gouging area and can be explained by the Kelvin-Helmholtz hydrodynamic instability theory. Due to this instability of the molten pool, the velocity of the liquid metal at the front of the molten pool is lower than the shielding gas velocity. The factors that affect this instability are layer thickness, velocity of the shielding gas, power, scan speed, hatch spacing, and feed rate. Also note, cross-sections of the welds can further reveal wetting angle, depth of penetration, height of reinforcement, and the shape of the weld pool. Dilution effects of the base metal and weld can be determined with chemistries and geometric measurements. So lastly, let's look at this image B here. So we can see as travel speed is decreased, the humping phenomena decreases too. Cracks and delamination are another important problem to address in metal additive manufacturing. These problems can cause premature part failure. Here in image A, we see a long crack. Typically, these long cracks not only go through the top layer, but multiple layers that are laid in the final build. Image B shows a short crack. Typically, when we see short cracks that are more shallow, they're only related to the top layer. And C, this is delamination. This image here on the right shows the different zones in a weld pool, and this will be useful in our discussion here in a moment. So there are three main types of cracking in additive manufacturing of metal parts. Like welding, solidification cracking, also known as hot cracking, can be seen along grain boundaries of the part. This type of cracking occurs because the solidified deposit tends to contract due to solidification shrinkage and thermal contraction. The tensile stress is generated at the solidifying layer, and if it exceeds the strength of the solidifying metal, then cracking may be observed along the grain boundary. Some nickel superalloys have seen solidification cracking even while the energy density processing parameter is optimized. Thus, the need to understand the effect of the metallurgical solidification temperature range and residual stress contributors in hot cracking is critical. Another known welding-based cracking seen in metal additive manufacturing is liquation cracking. This is typically observed in the mushy zone. Here we can see the mushy zone at the back of the weld pool, or the partially melted zone which is here on the side of the build. In the partially melted zone, rapid heating occurs to below the liquidus temperature of the alloy, and this can cause the melting of certain grain boundary precipitate phases. Then upon cooling, the partially melted zone experiences tensile stress due to solidification shrinkage and thermal contraction of the deposit. The liquid films along the grain boundary phases can act as cracking sites. The alloys exhibiting wide mushy zones, such as nickel-based superalloys, and large solidification shrinkage, such as Ti6-4, and large thermal contraction, or high coefficient of thermal expansion, such as aluminum alloys, are the most susceptible to these liquation cracks. The last type of cracking is known as delamination. This is caused by residual stresses at the layer interfaces that exceed the yield strength of the alloy. Cracking is dependent on alloy and composition, and EAG can help with identifying the type of crack, but also what is causing it. Printing defects can also be minimized by understanding the process science of metal additive manufacturing. Here, in image A, we see a keyhole-induced porosity. In image B, we see lack of fusion pores, and also gas-induced porosity, which is more spherical and comes in various sizes. Porosity and lack of fusion voids are common in metal additive manufacturing that need to be eliminated, since they can negatively affect the mechanical integrity of the final part. There are three main mechanisms from which these defects are produced in metal additive manufacturing. The first one, when operating at very high power density, deposition may be performed in keyhole mode. However, in this keyhole mode melting, keyholes can become unstable and repeatedly form and collapse, which can leave voids of trapped vapor. The second one, as we have seen before, gas can be trapped inside the powder particles during the manufacturing process, and they become entrapped gases in the solidified part. Additionally, gas cores can be formed as trapped gas or vapor alloy inside the molten pool. The last mechanism is for lack of fusion defects, which can be caused by insufficient penetration. So here, let's look at more of the defects. In this top row here, we can see this is different optical images for varied scan speed. So in image 1, we have a scan speed of 250 millimeters per second. Image 2 increases to 500. Image 3 increases to 750. And the last image is at 1,000 millimeters per second. So here we can see as scan speed increases from left to right, the molten pool size decreases, and then the print becomes more susceptible to forming a lack of fusion porosity. Here on the bottom images, we can see image 1 here. This is a variation of laser power. So laser power in image 1 is 90 watts. And in image 2, it increases to 120 watts. And in image 3, we're at 180 watts. So here, from left to right, as laser power increases, porosity can be reduced by increasing the molten pool size, thereby the depth of penetration. Besides using traditional techniques such as optical and SEM imaging, 3D techniques such as computed tomography are available to render 3D understanding of the location of defects and determine patterns based on scan strategy, bead morphology, and so on. This is an example using in situ synchrotron computed tomography mechanical testing to observe the defect growth of a low carbon 316 powder bed fusion selective laser melted final build. as compared to the wrought. Here we have the wrought, the low porosity, and the high porosity additive manufacture builds. And we can see that failures are initiated at defects related to the layer spacing of the build. Both 2D X-ray and 3D computed tomography is available at EAG. So now let us move on to talk about different alloy systems and the microstructural effects of additive manufacturing process science. Microstructural evolution and characterization are important to understand in order to achieve a viable printed part. Nickel-based alloys, titanium alloys, aluminum alloys, and stainless steels are more commonly additive manufactured systems. So in the next few slides here, we will give some examples of the different alloys and how important it is to correctly characterize their microstructure to achieve the desired results for the final part. Additionally, the chemistry and thermal histories both affect the evolution of the microstructure. Unlike traditional manufacturing processes, metal additive manufacturing are characterized by fast cooling rates, repeated heat cycles, and cooling cycles, which greatly affect the microstructural development. So these images here show the microstructure of CMSX-4. This is a nickel-based single crystal superalloy. It has 3 weight percent rhenium and 70% of the volume fraction of coherent gamma prime precipitate strengthening phase. The gamma prime phase precipitates when the temperature exceeds 1223 Kelvin. Different layers are subjected to different thermal cycles during processing, resulting in gamma prime size being different in different locations within the printed part. The precipitates at the bottom of the sample are exposed to more thermal cycles and longer periods. Thus, there is coarsening. Now, as you travel near to the top, it is more refined. So these images are a function of the distance from the top of the print. So at the top of the print, this is 0.5 millimeters from the top of the print. The coherent gamma prime precipitates are small. And as you go further away, because of the repeated thermal cycles and longer periods, which allows longer periods of coarsening, you get larger coherent gamma prime precipitates. Now this SEM image is of an Inconel 718 that is direct energy deposited. Intermetallics, such as laves and delta phases, are known to adversely affect mechanical properties in nickel-based alloys. These eutectic products are observed at the interdendritic regions or grain boundaries. Lave phases form in niobium-rich liquid, and the microstructure by the niobium segregation and distribution. The formation of intermetallic compounds is highly influenced by the solidification process. Lave phases are observed in connected chain morphology and can induce hot cracking in metal additive parts. Here we can see this in the SEM image. The understanding of formation of precipitates and intermetallic compounds in nickel-based alloys is critical for a successful additive manufacture final build. Next, we will look at titanium alloys. So at room temperature, we know that Ti-6-4 is mostly hexagonal, close-packed alpha phase and a body-centered beta phase. In metal additive manufacturing, the alpha phase transforms to beta phase during heating when the beta transist temperature is exceeded. Upon cooling, depending on the rate of cooling rate, if it is slow, then it transforms back to primary alpha phase. And if it is fast, then martensitic alpha prime. So here are some examples of the microstructure of Ti-6-4 when you're produced with different processes. So image A here is made via direct energy deposition. Here we see fine lamellar Whitman-Stanton structure and a small amount of this alpha grain boundary phase indicated by the arrows here. Now in image B, this is made with powder bed fusion electron beam melting. This produced a columnar prior beta grain delineated by alpha grain boundary. Now inside the prior beta grains, we see transformed alpha and beta microstructure, where two different morphologies are observed. The Whitman-Stanton, and then you see alpha colonies. In image C, this was produced using powder bed fusion selective laser melting. We see this lamella structure. In image D, this was made via direct energy deposition gas metal arc. We see alpha phase lamellas in the gray and a beta matrix beneath as white. So we can see from the microstructure that the cooling rates were slower since we're not seeing martensitic alpha prime here. So now we can look at some faster cooling rates where we do see that martensitic structure. So in image A, using powder bed fusion electron beam melting, this optical image shows top layers of orthogonally oriented martensitic needles. The lower layers here show a mixture of these martensitic needles and this featureless region of beta phase. In image B, using direct energy deposition, the microstructure shows alpha prime martensite. Here you can see the lathy martensite. In image C, using powder bed fusion selective laser melting, we see this acicular alpha prime martensite. So next, we will show an example of aluminum alloy in additive manufacturing. So the most common aluminum alloys printed are the eutectic aluminum silicon alloys and the hardenable aluminum silicon magnesium alloys. The microstructure of aluminum silicon alloys consists of primary aluminum and eutectic, fully eutectic, or a mixture of primary silicon and eutectic, depending on the composition and the solidification conditions. The microstructure of the aluminum silicon magnesium produced by powder bed fusion selective laser melting is typically cellular with some occasional side branches. The cellular primary aluminum is decorated then with silicon particles and magnesium silicon precipitates. The fine structure produced is high in hardness and typically doesn't require any post-processing treatment. Here we see an aluminum 4047. This is an aluminum silicon alloy. These were made using direct energy deposition via a laser. These optical images show columnar dendrites and equiax microstructure. Here we have columnar dendrites and more equiax microstructure. But they're in different regions of the printed pool, depending on the local thermal cycles. The primary aluminum dendrites are bright, and the aluminum silicon eutectic is gray, and they coexist in the microstructure. So here we can see this region. This is then blown up a little, and then two more images are taken. This one is here. Here we see the more columnar dendrites. And then in this region, we see a more equiax microstructure. So now let us take a quick detour into some theory on what dictates morphology and size of the solidification structure. So in this graph, we can see on the x-axis is growth rate, delineated by R. And in the y-axis, we have temperature gradient, G. So G over R determines morphology of the solidification structure. So as G is high and R is low, right, the ratio, we have planar. And as it becomes smaller, it goes from planar to cellular to columnar dendritic to equiax dendritic. Now, the product of G and R determines the size of the solidification substructure. So here we have, at higher cooling rates, which is the product of G and R, we have finer structure, right? And then here, at lower cooling rates, the product of G and R, we have a coarser structure. Now let us go back to the metal additive manufacturing of stainless steels. The most commonly metal additive manufacture of stainless steels are austenitic stainless steels, precipitation hardenable steels, Maurer aging steels, and soft magnetic high silicon steels. The most common microstructure of additive manufacturing austenitic stainless steels are cellular cells and columnar dendrites. Equiax microstructure is rarely reported due to the high temperature gradient in metal additive manufacturing processes. So here we have an example of 9 layers of austenitic stainless low carbon 316 using laser direct energy deposition. Here in image A, we have the lower region. In image B is the middle region. And in image C is the top region. So you can see in image A, it's finer, and in image B, it's slightly thicker. So the structure is primary cells, and the size of the cells increases with depositing height due to the accumulation of the heat cycles during additive manufacturing. Next, we will talk about mechanical properties in metal additive manufacturing. The most commonly studied austenitic stainless steels made by metal additive manufacturing are 304, low carbon 304, 316, and low carbon 316. Typically, the additive manufacturing processes used for these alloys are powder bed fusion selective laser melting and laser direct energy deposition. Typically, the additive manufacturing stainless steel exhibit high yield strength, ultimate tensile strength, and lower ductility when compared to traditional manufacturing processes. This is because in metal additive manufacturing, the effect of refined features, increased dislocation density, increased residual stresses is due to the high cooling rates, i.e. the rapid solidification. So here, in these two graphs, the one on the left, the x-axis is linear heat input, and the y-axis is yield strength. So here we can see as linear heat input is increased, yield strength is decreased. And the graph on the right here, on the x-axis, we have linear heat input, and on the y, ultimate tensile strength. And as linear heat input is increased, linear tensile strength is decreased. So at lower heat input, it results in smaller melt pools, high thermal gradients, and therefore faster cooling rates and finer microstructure, giving the higher yield strength here and the higher UTS here. Besides using tensile testing, hardness is an easier and faster way to understanding the mechanical integrity of metal additive manufactured parts. So here we have in the x-axis the linear heat input, and on the y-axis Vickers hardness. So as linear heat input increases, what happens? Vickers hardness has a slight decrease. Okay, this is expected because at higher heat input results in large molten pools, higher peak temperatures, and therefore slower cooling rates. And thereby hardness will decrease with increasing linear heat input due to more heat accumulation, larger grain size, and microstructural coarsening. This scatter that you see here can be attributed to differences in equipment and techniques, Additionally, you want to make the distinction here with low carbon, lower amounts of carbon, there's a change in the microhardness. Metal additive manufacturing can be studied more intricately using electron backscatter diffraction. So the use of grain refiners during powder bed fusion additive manufacturing is expanding. This is used to decrease cracking susceptibility and increase mechanical properties of aluminum alloys. So here in this image, on the left, we have an aluminum silicon alloy with no grain refiners. Then on the left here, we have that same alloy, but we add in a titanium diboride grain refiner. Okay, so this print is built via powder bed fusion selective laser melting. We can see the the efficiency of the titanium diboride in refining the microstructure here on the image on the right. Additionally, the texture changes significantly to a more random crystallographic orientation than here on the left, where you see a more preferred crystallographic orientation. Here's another example of doping using electron EBSD. So here, the top image is here. This is an aluminum silicon alloy. Okay, so image A here has no grain refiners. So now we see these larger grains. And then image B here, we use 0.33 weight% Tibor to refine the grains. This is a known commercial titanium boron grain refiner. Image C shows 0.4 weight% scandium refiner used. And the scandium is actually less refined than the Tibor. On the bottom here, we have an aluminum 6061 alloy. Here we have in image D, we have no grain refiners, nice big grains. Image E, here we use, again, the Tibor at 0.33 weight%. We see this tremendous grain refinement. In image F, we use 0.4 weight% scandium, and we see a grain refinement, but less intense than that of Tibor. So in conclusion, process science of metal additive manufacturing needs to be understood in order to create desirable printed parts. Correlation of processing parameters and mechanical properties through controlling the microstructure and the defects is critical in creating the desired metal additive manufactured part. EAG offers metallurgical services to assist in the analysis, testing, and optimization of additive manufactured products and parts, as well as years of metallurgical and materials consulting experience to help you create the highest quality parts in a cost-effective, optimized process. Here's a list of the references that I used for this presentation in case anyone's interested. So feel free if you need to read up more on what I talked about. And lastly, so you might ask, why do you want to choose EAG? Well, there are several reasons, but I think it is most important to state right at the top that client confidentiality is core to our business. We are a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. Finally, in light of the pandemic that is affecting us all right now, I want to stress that EAG Laboratories is committed to the safety of our staff and clients. Worldwide, we have compiled with the latest COVID-19 regulations from state and local governments, as well as the Center for Disease Control. Currently, all our locations throughout the world remain open, but we may have limitations on customer visits. As this is a fluid situation where we are operating a laboratory at reduced capacity, we can also transfer your samples to another EAG location. We encourage you to discuss your options with our sales representative.